Welcome to my talk about lost in transaction, or basically about avoiding getting lost in transactions. What we see today is that most applications that we build are at least in some parts distributed systems, and that poses a lot of new requirements, which, at least to my observation, is not every developer is fully aware of, and not everybody is equipped with the right strategies to handle that. And that's what I try to at least change a little bit in that talk. More or less 10 years ago, a bit more, I guess, there was a book called Domain-Driven Design, which is quite hype at the moment. And it's a pretty good book, pretty decent book, and it defines a couple of concepts that are helpful to understand, also to tackle consistency and transactions in systems. If you build a software, it's pretty likely that you will at least talk about entities. An entity is something which has its own identity. And domain-driven design also defines something which is called a value object, which doesn't have an own identity. So you can't reference an order line item. You can say, I want to have this order, but you can't search for a line item specifically. It's just like always belongs to the main entity. You can have multiple of these entities, multiple of these value objects. That's kind of, I think, pretty natural to how we build software. Now, what domain-driven design defines is what's called an aggregate. And an aggregate is quite an interesting concept because it's kind of a transaction boundary. I'm coming back to that in a second. So you could say something like, I have my order aggregate, and I have a customer aggregate. Probably I have a couple of more entities. We come back to that in a minute. In the same aggregate. But, and that's the important thing, this aggregate is a boundary. And what you can't do, you can't reference between boundaries by the mean of, for example, references in, for example, Java or whatever you use. Yeah, Devnexus, Java, probably. So you can only use IDs. So in this case, you could say, hey, the order belongs to the customer with that ID. And that's a string field, for example, for the customer ID, which is there. So you have a logical reference, but you don't have a technical reference there, right? That's super, super important. And you might have other aggregates like the charge. Now, I mean, so far, so good. If you take that one step further, you might have requirements where you touch multiple aggregates. Like you say, for example, you want to create a charge and you want to mark the order as paid. And then you have requirements that this is a transaction, a business transaction. So it has to happen all or nothing. If you can't mark the order as paid, you don't want to create the charge, for example. Right? Like once upon a time, like in the good old monolith days, you could simply use a transaction manager to do that. So if you have like everything in one database, for example, you can easily say, hey, I want to have this transaction begin here. I create the charge, I mark the order as paid, and then I commit. If there's something weird, I roll back the whole transaction. Right? That's what databases can do for you. This transaction is basically an ACID transaction. So it has ACID properties. They are defined, and you probably learned that in university, as atomic, so all or nothing, consistency. Talk about that a bit later on, but it basically means that the data itself is always consistent. So not null constrained in a database, for example. Avoid that you add data that's not consistent with that definition. So that's one thing. Isolated, that's one of the most important properties. Actually, we will look at that later in more depth. So it means if you have two threads, for example, they try to access the same data, one only sees the data once the other transaction is committed. Before it's not committed, it's not visible from another thread, for example. You can adjust that by isolation levels of a database, but that's kind of the default. And durable, I mean, it's a database. It should keep your data. So that's an ACID transaction. And if you have these aggregates, there are consistency boundaries. So you can do ACID transactions within one aggregate. That's no problem. You can update the order and the order line item in one transaction. No problem. But you cannot do a joint ACID transaction. And that's really important. And there's one advantage of that. So it really means that you can use different databases, different database technologies, if you like, right? But the main driver is really that you can evolve different parts of the system independently. You can scale that independently. You can have a different team looking at it, and all the things you might know from microservices, right? So if you have different microservices, per definition, they can't have a joint aggregate, right? So you always have this transaction boundary in between. And that's super important. That's super important. And that has a couple of consequences. One important note, and I find that really important because somehow it's sometimes forgotten. These boundaries, they're nothing which are totally carved in stone. This is how you have to define a boundary. It's a design question. It's part of your architecture, how you design the boundary. So you could say, I want to have the charge and the order, both entities in one aggregate, because I want to leverage asset transactions from my database because it makes programming super easy. And that's a valid reason. And if that doesn't have other negative implications, that might be the best design actually. So that's valid. You can design that, right? But it's a decision you have to make consciously. But if you have charge and order in different microservices and different aggregates, they can't do a joint transaction, right? This is what you should never do. I see that happening regularly. You should not. For a lot of reasons. It's not isolated. It's an implicit constraint. So you might change something here, which breaks code over there without you knowing it, and so on and so forth. Sometimes people now stand up like, hey, but there's two-phase commit. There's distributed transactions. So you can have a distributed transaction spanning different microservices, even remotely. Or there's stuff like Google Spanner or whatever. There are a lot of things. Distributed transactions or XA or two-phase commit or three-phase commit normally work with a transaction coordinator that does that in multiple phases, like asking everybody, hey, can you do that? And don't want to explain that in detail, actually. The important thing for me to remember about distributed transactions is they don't work, or you should assume they don't work for you in your scenario. There's an awesome paper. It's this one, Life Beyond Distributed Transactions, from Pat Held. He worked at Amazon at that time, and basically the summary is grown up, don't use distributed transactions. That's his own quote, so I'm safe here. So you should assume that. And there's I love this blog post actually from choreography. He wrote about Starbucks does not use two-phase commit. And it explains very well why also this is so important. So if you don't think about Starbucks, but let's say the bakery around the corner, and you go there, order a coffee. It's kind of, you go there at the cashier, you order the coffee, you pay for it, and then the person really does the coffee for you, right? And everything is blocked. If there are people behind you, they have to queue, they have to wait, even if the coffee takes a long time to make, right? And this is not how Starbucks works. If you walk in, you basically order with one person and pay, and that's it. And then you're put into a queue, like in front of the barista. The baristas, you have probably 3 or 4 people, so they are scaled independently, right? And then at the very end, the coffee is again put in a queue with a correlation identifier, which is your name, in order to be delivered to you. And that whole system works pretty well, actually. It works much better. It scales better. You don't queue that long. So there are a lot of advantages to that. But it's not transactional. I mean, if you don't get the coffee, the money is already gone, right? You can't roll back that. But there are things you can do about that, like you complain and then you probably get a bigger coffee or whatever. So it works pretty well in reality. And that's kind of the mindset we're trying to get to, right? Eric Pruer, one of the Google persons, basically, he said in a keynote already in the year 2000, I find that pretty remarkable. He said, we have to forfeit C and I, so C and I from asset, in order to build systems that are available, that degrade gracefully if something is broken, but still other parts are working, and they are performant and scalable, right? And this trade-off is fundamental to build these kind of systems. And he named that base that never took off, basically available soft state, eventual consistency. So that acronym never took off. But the idea is totally right. And he said that already in the year 2000. So it basically means to say we do two activities. They're like they might have local asset. So every activity in itself, it's asset. But in between, we have an inconsistent state because we say, hey, A has happened, but B, we don't know what will happen with B, if it succeeds or not. But that's okay as long as we restore consistency at the very end. Right? That's why it's called eventual consistency. Okay. And this is what's happening in DDD with aggregates, with different aggregates. In the microservices, well, that's the default because you have different microservices. But it could also be that you have different programs, different resources. If you use, for example, Apache Kafka, you can't use that in a joint transaction with your database. You have two different resources, and they can't do a joint transaction. So you have that problem all over the place nowadays. So it really is important. And it, by the way, and probably it's my type of humor, but I find that funny. This eventual consistency, it violates not the consistency constraint of ACID, but the isolation constraint, right? Because it's not isolated. The data is fine, but if somebody reads it here in the middle, he sees something in the middle, which he shouldn't. So it's not isolated, right? We have to learn to live with that. Pat Helland also wrote a paper about that quite a while back. At that time, he called it ACID 2.0. So 2.0 was the thing back then. Right? Nowadays would be ACID 4.0, something like that. He said, but we have to change what the acronyms are standing for. So it's associative, commutative, idempotent, and distributed. That's what we have to do. So associative is basically like, from math, you can change the sequence of things. That works. Commutative is like, yeah, more or less the same thing. So I will not talk about these two here today. But I want to talk about the other two, actually. Idempotency, which basically means you can do it twice without doing any harm, and distributed. And the distributed part, that's the part which is kind of the given scenario nowadays. That's not a choice. We do most systems in a distributed fashion because it doesn't work otherwise anymore. We have to call services from other companies, from other departments, on other containers, other machines, and so on and so forth. This is my favorite metaphor for distributed systems. So if this is your one program, your one microservice, there you're doing something in Java, it's cozy. You have ACID, yay. You have a heating, cool. But when you open the door, there you have the rough ocean, which is the network, and that will fail you at the time where you don't need it at all, right? So that's a distributed system. Probably you know that. I hope you know that. If not, look it up. The fallacies of distributed computing. It's really like, and the top one, and I think it's really the top one, is the network is reliable. It's not reliable. We program very often in a way as it would be reliable. As we do a REST call, it looks in the Java code, it looks like a local method call, but it's so different. And we need to make this something we are really aware of in everybody head. And I give you a problem. I give you an example. Let's say you have a payment service and that should do credit cards. Credit card handling is normally not done by you internally, but you leverage a SaaS credit card service like Stripe. Has a REST API. Now let's say, and this is even the internet, so it might fail at sometimes, or they have an outage or whatever, right? So you need to retry things. That's the first thing. That's important. You retry. You try to chart it. It doesn't work. You try to do it again if there was a network problem. Okay, that's the first thing. You have to implement that. A lot of frameworks can do that for you relatively easy. But the important thing here is, in order to be able to do that, the other party, the credit card service, has to be idempotent. What does idempotency mean? It's relatively easy. It basically means that you can do the call twice and the effect doesn't change in that sense. So if you charge the credit card with the first request and then you retry it, you don't charge it again. And it's relatively easy to get to that state, which normally means you have kind of a transaction ID somewhere in your API. And the transaction ID is generated by the client. And if you do the retry, you retransmit the same transaction ID. So the credit card service can see, oh, I already saw that. I don't process it again. Relatively easy. It normally means you have to keep transaction ID in some kind of state here. And it means that the transaction ID has to be generated as soon as possible and transferred or transmitted with every API call, which means you have to add it to your API. And that's the important thing here, right? Because if you don't have this, and a lot of legacy APIs don't have this, then that's really a huge problem, because now the credit card service, I mean, it could guess, hey, you charge the same amount for the same credit card within a very, very small time frame. That might be a duplicate, but you don't know. You guess. And that's a bad situation to be in. So that's super, super important. I'm a metaphor person. So I thought about a metaphor for idempotency, and that's, sorry for that, but that's the best I came up with. So if you have better ideas, let me know. It's zucchini, yes. Why? Because one of my favorite dishes are zucchini noodles. So it's really, you take the zucchini, have a slicer, a special slicer, special device, and then you get noodles out of that zucchini. And then you add some pasta sauce, basically. It's awesome. I love it. And the good thing about that is you can eat as much as you want. It's even in the cookbook, like eat as much as you want. It's my very easy explanation is like it's basically water. So you can eat as much as you want. So if you ate your plate of zucchini noodles and then you forget, if you already ate a plate of zucchinis, you simply eat another one. No problem. Oh, forget again. I eat another one. No problem. It's totally idempotent to eat zucchini noodles. And that's very different to pasta. Okay. And yes, I know it's kind of a silly metaphor, but it's the best I came up with so far. It's challenge accepted. If you have good ideas, let me know. The important thing for me is that it sticks, that you really can remember. That idempotency is so important. If that's the only thing you take away from this talk, that's fine with me. Okay. So if you implement a service, provide an API, make sure it's idempotent. Make sure you add that transaction ID, correlation ID, whatever it is in your scenario. But don't guess on business data. But that's not all. If you have distributed systems and you have a network exception, and that was kind of part of the example we had, and you get a network exception, you have no idea what just happened. And it's important to understand that. So you might never reach the credit card service. You might have reached it, but it exploded during doing something for you. Did it like commit its transactions? You have no idea. Or was the response lost? Yeah, could be. You don't know, right? And that means you also have to plan for this. So for example, if you charge the credit card, even if you get an exception, you might have charged a credit card. So you have to do something. It could be that you simply say, okay, I undo the charge. I check if something was charged. That depends again on the API. The service has to provide something for you to do that as a client. But as a client, you have to do it. And that's super important, because a lot of it's surprising how often I see people that, yeah, but I got an exception. I didn't call the service. Hey, you might have. You don't know, right? Okay. Because we're in distributed systems, some of these solving this might require state. So coming back to that example, if you get an exception while charging the credit card, it's pretty likely that it's not available as well when you try to clean it up. So you need to wait for the service to become available, either for doing retries. So you might want to wait for the service to become available for the retries for some time, for minutes probably, or at least for the cleaning up, you should wait. And then you get a stateful problem, because you have to remember things in a database, for example. right? You can retry in a millisecond in a thread, but you cannot wait for a minute or 5 minutes or an hour. And that's actually kind of my domain. That's why I'm thinking about that all day long in a way. Or the other way around, probably. That's why I'm got so hooked up in the topic of workflow engines. So I'm Bernd Ruecker. My name. I'm co-founder of Camunda. We're an open source process automation vendor, and I'm doing workflow engines and stuff around that for the last more than 15 years, actually. I committed to a couple of open source engines in the past. I wrote 2 books. I'm currently in the last steps of publishing Practical Process Automation with O'Reilly. If you want to reach out to me even later, there's my email address, there's my Twitter handle, tweet about a great talk if you like it, and so on and so forth. But that's, of course, also my bias. I look at problems from the perspective or through the lens of state machines of workflow engines, right? That's important to know. But you can now use these kind of engines also to solve these stateful problems like retrying. A workflow engine could do something like execute a very simple process. So you can model that, or you can even write it in code. It also depends a bit on what tool you use. And then it can wait in certain steps for even days and retry periodically. So a workflow engine has kind of a scheduling capability built in, and then it can do that. And it even, like on a code level, you can imagine it like this. So that's the example I used in the book. So if you have a workflow engine, you can, for example, start a process instance for payment whenever you retrieve the REST call that you should retrieve payment. And this instantiates a new process instance, which basically means that's written to a database table. I mean, that depends on the product, how they persist exactly, but this is how you could imagine it. It's persisted there, and it remember where it's currently waiting at, right? And then you can attach code to certain tasks in that process model, like charging the credit card, which is more or less exactly the code you would write anyway. But now you have the capability of waiting and retrying and monitoring things and so on and so forth. So that's pretty awesome, actually, and gives you a lot of possibilities. Also, do cleanup, for example. Hey, I can't charge the credit card, so I erase a payment failed response, for example. But then I have all time of the world to clean up. And if that takes longer, no problem. The workflow engine can handle that. And that's already already a strategy to cope with these inconsistencies or these eventual consistencies I have in distributed systems, because this makes it eventual consistent. But that's, I totally agree, is still a very simple example. You can do much more with these kind of technology. Just architectural wise, I see this logic here, these process model as domain logic. So instead of writing it in Java code, you probably express certain parts in a process model, because that makes sense. And then you need the infrastructure like a workflow engine in order to execute that, right? And that can be very simple, actually. If you look at GitHub examples I link in the talk, you can see that if you're in Spring Boot, you might run the workflow engine as a Spring Boot dependency embedded in your Java application. If you're in the cloud, we have a cloud service you can easily leverage, and so on and so forth. So it's 2021. It's not so hard to run a workflow engine and leverage long-running capabilities. In the in my case, in the example I linked, I use Camunda by coincidence. That's the company I co-founded and the best engine in the world, probably. But hey. But let's go back to the topic and acid. That's interesting. And I love this book. I can totally recommend it. It's one of the best books I read in quite a long time, I think. Designing Data-Intensive Applications from Martin Kleppmann. And he also gives talks. And I love that talk from 2015, quite a while back, but it didn't change much from Strange Loop. It's on YouTube, so you can look it up. And he had one slide where he said, okay, without cross-service transactions, so no XA, right? You remember the beginning, I hope. No XA. No distributed transactions. So then you have to do either compensating transactions, so a rollback at the application level, or apologies. Basically ignore the problem, but you detect it afterwards and then you apologize. I don't want to talk about this today. I don't have much time, but it's kind of overbooking your airplane and then like giving out vouchers or whatever if it really something weird happens. But I want to talk about compensating transactions, which are really interesting. And one of the classical example, and if you Google for the problem, if you read through the literature, you will always find this example. That's why I'm using it as well, is trip booking, right? Okay, it's COVID times. It's probably not the most common thing we do nowadays, but come back, hopefully. But the example is like you book a trip, which includes booking a hotel, booking a rental car, booking a flight, right? And you want to build a service doing that. And this uses external services. So if, for example, you can't book the flight for whatever reason, you can't simply roll back the rental car booking, but you can undo it. It's kind of a semantical rollback, an undo on the application level. It really means I cancel the already booked car, I cancel the hotel. Okay, and then in the very end, I'm consistent again eventually because I don't have anything for the trip. Okay, that's the whole idea. That's also very often known as the Saga-Pattern. That term gets quite famous recently. So that's Saga-Pattern. That's also what you can Google for. It's originally a paper from the 80s about long-lived transactions, but it's kind of how we discuss it at the moment. And now there are two approaches to implement that Saga-Pattern, which are both interesting to look at. The first is choreography. So you could have events flowing around, something like, hey, I want to have that trip. Okay, so the hotel service goes ahead and books the trip, so the hotel is booked, and then the rental car service could say, oh, if there's a hotel booked, I have to book the car, and then the car is booked, and so on and so forth. So you get a chain of events. I'm not a big fan of that either. I have a couple of other talks explaining why. In this case, you also have to, in case of a problem, you basically go reverse order. Like, hey, the flight was canceled. So the rental car service needs to undo or cancel the car. And this produces an event and so on and so forth. So you go the reverse way. And that's still an approach which is, let's say, advocated very often in the microservices world, at least. I have a couple of issues with that. The most prominent one is you don't understand it. I mean, you don't see what's happening. And I was super happy when Martin Fowler also blogged about that in 2017. He said the danger is that it's very easy to make nicely decoupled systems with event notification without realizing that you're losing sight of a larger scale flow and thus set yourself up for trouble in future years. So it might not be the really good idea. And there are a couple of other sources in the internet pointing you to the problem. And you can make a thought experiment of adjusting the sequence, like, hey, we can now book rental cars or we can cancel them for free. So we want to do that before the hotel because it gets cheaper for us, right? So we want to change the sequence. Now think about you have to touch each and every component in order to make it happen. You can do that as homework to try it out. It's quite hard to do such a change. So that's why I'm not really a big fan of choreography in that case. And this is how I typically see it. Like choreography is very often advertised with that beautiful dance where you can add new dancers and they will behave according to the rules and it will be a beautiful dance and not what I see in reality where it quickly leads to chaos actually, which is hard to understand, hard to change. What's the alternative? Orchestration. So you have you want to have the trip. So the trip is coordinating the others, saying, hey, now book the hotel. Okay, it's booked. Now book the rental. Okay, it's booked. Now book the flight. Okay, it's booked. Right. Much easier to control. And now they have that fun place where you can do changes. And because it's normally distributed, it needs to be long running. And that's why a workflow engine is a superb possibility to implement sagas. Because now you have it long running, you have the sequence. In BPMN, which is the standard I'm using here, the language, you can define these compensations where you say, hey, if this activity was done in the past, please do this in order to undo it. You can define that in the model and then the workflow engine takes care of doing the heavy lifting. Cool. If you want to know more, there are a couple of talks. I recommend this one. I loved it from Katie McCaffrey. At that point in time, she was at Twitter. thinking about sagas a lot. Cool. Yeah, this is more or less what I wanted to share here. I'm a huge fan of graphical models, by the way. So sometimes people doubt that, but I always use that. Article is quite old from Clemens. I'm sorry, Clemens, to use it again. But he described the same problem of a saga and how he implemented it, like there, and there. And what you can see is he started with a picture. So it's very, very useful to have these graphical models to understand certain consistency problems because you have to solve it on the business level anyway, right? That's why I'm such a huge fan of these graphical models, which are really living documentation. Yeah, and then you can also use that in operations and analysis and so on and so forth. So that's pretty cool. As a recap, aggregates are consistency boundaries. If you cross them, don't use distributed transactions. You have to have other strategies like cleaning up, retrying. Idempotency is super important to make all that happen. Saga and compensation is a very important concept you should be aware of. A lot of things get long running. That's why workflow engines are pretty helpful in that case. Thank you very much.